So this is the questions part of the review session. Another question is, what is an example of parallel heat flow? I can scroll up to that slide.
While Jackie's scrolling up to that, I'm going to start describing what an example of parallel heat flow is. So heat flows through a wall that has an area in all the possible places in that wall. And let's say the wall has two different makeups. On one portion of the wall, the heat has to go through certain materials like this. You've got a whole bunch of different materials listed under part C that the heat has to go through. And then under a different portion of wall, the heat has to go out through other materials like B or A. So there are many different paths that heat can take, and they all have different R values and U values to these particular assemblies. So first, what you do is you think about series, or you think about a series calculation for heat flow, which is to say heat running through a material with a particular R value, let's say material 1, and then through another material with a different R value, material 2. And so already the resistance of that particular path through the wall is going to be different from material 1 or material 2 alone, because it's a composite of those two. Then when you look at a whole building or even a slightly larger piece of wall or roof or whatever, generally speaking, it's not going to be all the same layers, because you've got wood framing behind there, maybe you have metal framing, maybe you've got, you know, some pipe that's protruding straight through the wall, which is a very easy path for the heat to be flowing through. And so then after you've done each of these individual paths in series, then you do them all in parallel, which is to say heat's not just flowing in series through a bunch of different R values, but it's flowing in parallel through a bunch of different parallel paths, each of which is made up of a different series of R values. How was that?
I think it was good.
It was good enough. It wasn't my segment. I love heat transfer too, though. It's really fun.
Mm-hmm.
Yeah, great.
It looks like there's another question about being able to put in what-if scores for the final. And I'm not sure I know how to do that, but do you guys know how to put in those what-if scores?
Yeah, you can go and simulate a final grade on B courses.
I believe the setting needs to be turned on, and I don't think it is yet.
Has it not been? I thought I saw somebody had done it.
I know you can.
Oh no, that was just,
you can't.
Yeah, maybe it hasn't been turned on. That's up to Gail. If she hasn't turned it on, then I think we don't have it. I might have just been looking at the example, the practice materials.
But you can go on like finalgradecalculator.com. That would be good for people.
Thanks, Preston. Any other confusing topics? All those different solar angles?
Okay, I have a question. Like Gail mentioned, like we can finish the final without taking the full 3 hours. But do you have any idea, like, is it 1 hour and a half enough for the final, or I should take the full 3 hours to finish it? Like I mean, like how long the length of the exam? You know, is it designed for like an hour and a half or something like that?
So it's definitely not designed for 3 hours, as you know. However, us as a review team, we are not privy to the exam because we're not supposed to tell you what's on the exam, so we don't know. So we don't know how long it's going to be. So sorry, we don't know. But
Right.
knowing Dale, she's definitely going to give you enough time, and yeah.
Thank
You
you.
should probably set aside the full time just in case. Have those 3 hours set aside so you can use them for the exam, but most likely it won't take the full time.
You can have
That's true.
some.
And then I guess if you want to do smart timing, you'll be able to see the number of sections and then take 3 hours, divide the number of sections so you know like the maximum time that you have for each section. I think that would probably be like a good way to plan for it.
Yeah, thank you.
Sorry to cut you off there. Dang, I should have gone over more etc. things. I feel bad.
Will there be any more office hours tomorrow?
Oh, I didn't even go to my office hours today. Crap. Sorry to my students if you came to my office hours. I was preparing for this.
I held my office hours today and no one came. But if someone would like to set up another opportunity to talk through things or go over the material, I'd be happy to set up a time for that.
Yeah, people might be in final reviews or preparing for finals, so probably just best to email your own GSI. It's going to be a really exciting part of the video. I hope no one's just like wait while we're just chatting here. But yeah, I've heard that this review is a pretty good overview of a lot of the concepts that will be on the exam. So, you know, you can slowly go over the slides later on. And yeah, that should help you at least give a brief outline, but I would still recommend going through all of your notes if possible.
And above all, take this material forward with you into your design of architectural conditions. I think that you'll find that this class is a real asset to you as you move into the professional world, because we're getting increasingly focused on this. The legislators are making it requirements, and there are a lot of people out there who aren't equipped to handle some of these problems that you're learning to deal with. So.
And there are a lot of office projects out there, and even housing projects. For offices, you want to make sure there isn't a ton of glare for computers. As we all know, that can be like a huge issue. And then for housing, it really helps to have passive shading strategies rather than having really expensive air conditioning costs, because in California, air conditioning isn't required, even though days like today, it's like you wish you had it, but you hopefully have a better envelope instead.
What was the temperature like where you are today, Jackie?
I don't know, it felt like 90, but I checked and it was like 83. But yeah, all of my windows are open for cross ventilation. And yeah, lower flow coefficient with just a dress.
Admirable application.
Constantly 140 geeking out.
No questions, huh? Whole lot of people here, though.
I know, we're just like hanging here with how many people? 50? Anyway, I think, okay, well, I guess good luck with studying, guys. You're gonna end it here. Oh,
Oh,
Is there time to go over a few short practice problems? Sure.
we did not prepare other ones.
Let's do it, though. Why
If you
not?
have
Right?
one. Okay, sure. Yeah.
I mean, we'll have to make up the problem. What topic would you like to make up a problem for?
Jeanette, since you're asking, yeah, is there any particular area you would like to practice?
Nothing in particular, just anything you guys would, anything would help, honestly.
Cool. I'm gonna pull up section slides. Maybe that will be easier than us coming up with a question all on our own.
that sounds good.
Oh yeah, don't forget to
See.
study the case study. That was a good question from one of my students. Case studies are still important to study. So we did not cover that here.
Okay.
Sorry, I thought I found a thermal math question, but I did not.
Why don't, can I share a screen, a blank screen, and then I'm just gonna draw on it?
Sure.
Sure, go
That's
for it.
gonna be fun. Okay. Can everybody see my blank screen? Pretty much blank.
Yep. Oh, you can change the background too.
You know, like the little dotted squares. I'm actually just even going to use this annotate because then I'm going to take it and draw it away. Okay, so I'm going to do some solar angle review quiz questions here. Ready for this? Here is
Yay.
the point in question and the surface of the Earth. A line coming directly south from the point in question. A sun shining in the sky. What is this angle? Directly south. The sun is directly south.
This is for you students, not for us. Hint, it's on your cloth back, bottom edge. Should we just tell them the answer?
Sure. Path.
Barbara said angle of incidence.
It could be described as the angle of incidence. That is a more complicated way of describing it. Normally, this would just be considered the altitude because the sun is south. it's also the angle of incidence. So bravo for having gotten that. The angle of incidence is a little bit more complicated because it describes the condition where the sun is here, but also it's slightly out of this plane, but projects to the same spot if you were to project it into that plane. Yeah, this is the solar altitude or angle of incidence. The angle of incidence, of course, would mean that it has to be relative to a wall that is facing east-west, if it's an angle of incidence. All right, let's do a
I
U
see what
value.
you're about to sketch, Eric. Actually, I have an example on my screen.
Great,
If that's
let's
okay.
do it.
It's a beautiful drawing, though.
Oh, thank you.
Okay, so this is what Sierra quickly went over. This is heat transfer in a series. So you need to sum up the resistances of multiple materials. So this is an example, finding the U value of insulation. You have all the stuff that you need right here. So U value is the inverse of R value. So you have that equation, U insulation equals 1 over the sum of the resistances. Then you go ahead and list all the different resistances you need to add together. So there is always air films, indoor and outdoor. So start with the resistance of indoor air film plus the resistance of gypsum plus the resistance of insulation, resistance of plywood. As you can see, you are not going through the stud in this arrow, so you do not need to add the resistance of the wood stud. Once you get all those values from this pretty little table, you get 20.92 hours foot squared degrees Fahrenheit over BTU. And then you take the inverse of that R value and you get 0.048 BTU over hours square feet degrees Fahrenheit. I would highly recommend that you use a piece of paper when you calculate this stuff so that it's easier to check your units.
If it'd be helpful, I could go over the one-room house example again, since I went through it pretty quickly and there are a lot of steps. If that would be helpful. I'm happy to go through that again, or kind of like in more detail.
If you guys want that, please raise your hand or give a thumbs up reaction. Hands up, 1. Okay. Ben, Pelosi, Brigitte. Okay, Brigitte, cool.
Cool.
Go for it, Sierra.
Cool.
Do you want to share your screen?
Yeah, I might try and just do it on the whiteboard. I'm not sure how well my writing on that will go, but
Okay. Make it easier.
so try. Well, let's see. Okay. Maybe I should. Well, first I will go back to the. Go back to the slides where it kind of explains the initial problem.
I have it if you want me to share.
Oh,
And
I
then
think
you can, or no, you got it.
thanks.
Okay.
Yeah, so this is like the original opening part of the problem. So giving a lot of information about the one-room house. So the goal here is to eventually find UA ref, the balance point temperature, the furnace size, the number of degree days for this particular climate, the weekly energy use, and the weekly energy cost. And so in order to do that, we get a lot of information right off the bat, which kind of some of it we use from the very beginning and some of it comes in later. So the weekly temperatures don't come in until we're looking at degree days. But when we're looking at like the footprint and the height of the house, the number of doors and windows, that's all coming in for the UA ref. A lot of this information is coming in when we're calculating UA ref. Internal gains and thermostat setting are important for balance point temperature. The cost of or energy gas is important for calculating that total cost. The furnace efficiency for calculating the energy use. So these kind of come in throughout. And then we are given these R values for the ceiling where there's framing, the ceiling where there's insulation, wall where there's framing, wall where there's insulation. So in this case, we're actually given some values that are a few steps ahead. So this is the total R value for that part of the ceiling where there's framing, and there's more than just framing. It's not just wood. There's, looks like from our photo, there's some kind of outer layer that's kind of falling apart. But most likely there are a few different materials, and they're also we're also kind of taking into account the air films for that R total too. So these values that we're given are already skipping a few of those steps, and we're given the total R value for that particular ceiling, portion of the ceiling for the framing, the different materials that are part of that, and those and the air films that correspond to it. So for the ceiling framing, ceiling insulation, wall framing, wall insulation, and the doors even, we're given those total R values rather than the individual R values that you would look up in a table for different materials within a wall buildup. Because this is already a long problem, so that saves us a little bit of time at least, but there might be other problems that focus on that part of the problem and ask you to get to that point. Cool, so maybe now I'll switch over to the whiteboard and see how that goes. Okay, so maybe I should have copied over everything. I'm not sure. I'll just go here and you can refer to the slides on B courses to look back at those initial kind of conditions. But so we start off, we want to find UA ref. And UA ref is equal to delta UA plus FP, which is the perimeter. So delta UA is the kind of conductive heat loss through the building envelope. FP is the heat loss due to the slab edge, and then also plus the kind of heat loss due to insulation. So I'll just put as I. So to break that down, so first we want to, I guess I could use colors too. Well, let's see. Maybe I'll start using color. So for UA, oh, is there a raised hand? Feel free to just shout out any questions you have as I go along.
Questions might be left over from them wanting the whole building.
Okay, cool. Sounds good. Yeah, if something does come up, you can just shout it out. So for delta UA, we want to sum up so I'm kind of assuming we've already calculated the areas of the different like ceiling framing versus areas of ceiling with insulation. And we knew that 15% of the walls and ceiling were framing. So we knew that the area of the house, it was it's 12 by 15 feet in terms of footprint, and then it's 10 feet tall. So we know that. So kind of assuming we calculated the basic geometry of the building, so breaking down all those areas of the different parts, and also the areas of the like area of the wall framing versus area of wall insulation. So we calculated all of those and broken it down by that. So in order to calculate the kind of sum of the UA values, we want to sum up the U of the ceiling where there's framing multiplied by the area of the ceiling where there's framing, plus the U value of the ceiling where there's insulation, multiplied by the area of the ceiling where there's insulation, plus the U value of the wall where there's framing, multiplied by the area of the wall where there's framing, plus the U value of the area of the wall where there's insulation, multiplied by the area of the wall where there's insulation, plus the U value of the windows multiplied by the area of the windows, plus the U value of the doors multiplied by the area of the doors. So we're going to multiply U value times A for each of those individual parts, which are all in series, or all in parallel, sorry, all in parallel. We kind of move past the part where we're calculating for each part the materials in series. And now we're looking at all these materials in parallel, we're adding U values. And so for each portion of the wall with a different material breakdown, we have a different term for UA. And so when we add all of those up, plugging in the correct numbers, I kind of am still skipping parts, but can trust me that we get 84.9, and that's BTU per hour Fahrenheit. Hopefully this is helping that I'm writing it out. If not, I can switch back to the slides. So let me know if this is just making things more confusing. But yeah, so, and then part 2, the heat loss due to the kind of perimeter slab condition. For that, we want to multiply the F factor, the perimeter edge loss factor, multiply that by the perimeter. And so that edge loss factor was 0.55, and then the perimeter was 54 feet. And so we get 29.7 BTU per hour degree Fahrenheit. And then last, for the infiltration, for that we want, I'm just gonna put it over here, up here. Infiltration is equal to volumetric heat capacity, which is given for air, multiplied by the volume of the space, which we calculated knowing the kind of width and length of the building and then also its height. And then multiplying that by the number of air changes per hour, was given as 1.1 air changes per hour. So from that we get 35.6 BTU per hour degree Fahrenheit. So that's calculating those 3 portions of UA ref. So then in order to add them up, I'm going to clear everything. So when we add those up, UA ref equals the sum of the UAs for conductive heat loss plus FP, the perimeter edge loss, plus I, which equals 150.2 BTU per hour degree Fahrenheit. So bringing those 3 numbers that we calculated, the 84.9 BTU per hour degree Fahrenheit plus 29.7 BTU per hour degree Fahrenheit plus 35.6 BTU per hour degree Fahrenheit. And so once we have that, we can start to calculate our bounce point temperature. I'm going to circle this very important number that we use in all of our following calculations. So now I want to calculate our bounce point temperature. So in order to calculate that, we set our internal gains equal to the heat loss through the envelope. So, and we know the heat loss through the envelope is equal to UA ref. It's a very handy number we calculated. And then for the case of this balance point temperature, where we're setting the internal gains equal to the environmental losses, where we're kind of like balancing out the internal gains versus the losses. In this case, our temperature change is the balance point temperature, which we're going to solve for, minus the indoor temperature we want to reach, which was given as like the thermostat temperature that we want to get to. So, so we want to solve this problem for the balance point temperature. So when we rearrange, we get that the balance point temperature equals the thermostat set point temperature minus the internal gains over UA ref. So the thermostat temperature was 70, the internal gains were 2000, so 70 degrees Fahrenheit. 2000, I think it was, BTU per hour. And then your UA ref from up here was at 150.2. And so together we get that the balance point temperature is 56.7 degrees Fahrenheit, which for the purpose of days later on, we'll round up to about 57 degrees Fahrenheit. Pause for any questions so far.
I'm just going to read out a question that I already answered, but you would be given the value for F. It would be for an insulated slab or uninsulated slab, and they might give you both values, but the question will specify what type of slab it will be.
Yeah, that's a good point. So especially in this kind of question, a lot of those kinds of values will be given at the beginning of the problem. So in this case, the F perimeter edge loss factor was given as 0.55, and it will be given on exam problems as well.
But I'd also like to underline something that Jackie just said, which is, you can hear me, right? I don't get the little green square on me right now. You might be given many more pieces of information than you need. You might be asked to calculate the U value of a wall assembly that has 3 different materials in it, and you're given a chart with 20 different materials. So you have to be able to identify the pieces of information that you're going to be plugging into these formulas. So don't just assume that because you're given a number, it's going to be useful. And that's where it's always helpful to look at units and to make sure that you're taking the terms of the question very seriously. Is it an insulated slab or an uninsulated slab? That sort of thing.
Yeah, that's a really good point. And it's good to double check that your units are canceling out. So in this case, we had UA ref as in BTUs per hour Fahrenheit. So degree Fahrenheit. So here, yeah, having a lot of canceling out of the units, and then we just have those degree Fahrenheit left when we're calculating our balance point temperature. Cool. So now I'm going to move on to clear this and move on to next part, which was calculating kind of like the peak heating requirement to be able to size the furnace. So switching to a new color. So in order to calculate the kind of heating load required, the peak max heating load required for the furnace, which we're going to use to size our furnace so that we know it can handle those peak conditions, we want to think about those kind of most extreme conditions. So we're using this design temp, which is 20 degrees Fahrenheit, which is pretty low. And in this case, we're thinking about only the heating regime. So when the temperatures are really cold, those are our most extreme conditions. So to be able to calculate the required energy use from the furnace under those conditions, we are looking for Q of the furnace, which is equal to Q peak, which is then set equal to our old friend UA ref. And then our delta T here is the indoor set point thermostat temperature that we want, that 70 degrees Fahrenheit that's comfortable, minus our 20 degrees Fahrenheit, which is kind of our extreme outdoor temperature. So then when we solve that out, plugging in that 150.2, we get that our Q peak equals 7.5 kilobtu per hour, Q dot peak. So it's the kind of rate of power energy input that we need during those peak conditions. Yeah, and nice unit canceling too. Cool, and so then going to degree days, maybe I can go back to the PowerPoint for this one really quickly. So yeah, when we want to solve for degree days, we are going back to the data that we were given on our average outdoor temperatures throughout this particular week that we're looking at. And so for degree days, we're looking at the number of degrees off from our balance point that the outdoor temperatures are. So for heating degree days, you're looking at how far below the balance point temperature, how many degrees below that balance point temperature you get each day. And you're not including any of the days when the average temperature is above the balance point temperature. If you were doing cooling degree days, you do the opposite and look at how many degrees over you're getting and not count the ones below. So you kind of separate those into the two categories. But for this example and for this class, we're really just looking at heating degree days. So we were finding that difference between the balance point temperature and these average outdoor temperatures throughout the week. So on Monday, the outdoor average temperature is 50, so the difference is 7 degrees. On Tuesday, it's 45, so the difference is 12 degrees. On Wednesday, 7 degrees difference between 57 and 50. On Thursday, Friday, and Saturday, the temperatures are 65, 60, and 60, which are all over 57, and so we're not counting those for our heating degree days. But then on Sunday, the outdoor temperatures come back down to 55. The average outdoor temperature is back down to 55, and so we have a 2 degree days from that day. So adding all those up, we had the 7 plus 12 plus 7 plus 2. So I think that should equal 28 heating degree days. So we use that to calculate, so we calculated degree days, and now we can calculate how much energy is being used over the course of this week with these kinds of temperature conditions based on the climate. Now I'll go back to the whiteboard. Yeah, and you no need to stay around. I'll just finish a few more. We're almost done.
I'm going to check out. I wish you all well. I leave you in capable hands. Goodbye, Jackie. Goodbye, Sierra. Goodbye, everybody else. I'm going to go have dinner. Good luck on the exam.
Thank you.
Cool. So just a few more sections. We're almost done. So then, knowing those degree days, so we calculate the number of heating degree days is equal to 28. So knowing that, we can calculate the energy used over the course of a week, this particular week where we calculated those particular heating degree days. So that's equal to UA ref, that 150.2 BTU per our degree Fahrenheit. BTU per hour degree Fahrenheit. And then multiplied by the number of degree days, which is 28. And then because we're using degree days here, but our UA ref is in hours, and our Q, if it were a Q dot or something like that, that would be per hour is BTU per hour. So we really want to transition to hours, so we know that there are 24 hours in a day. So yeah, we want to make sure to make sure all our units cancel out. So these are in degree days are in degree Fahrenheit day. So we can cancel out our days, cancel out our degrees Fahrenheit, cancel out our hours, and then we just have those BTUs remaining. And so when we calculate all those out, 150.2 times 28 times 24 gives us 100.9 kilo-BTU. So that's how much energy was used in this particular week with those heating degree days, that number of heating degree days. And then just kind of one more step. So we know that our efficiency is, which is equal to Q out over Q in. We know that that is 90% or 0.9. So we know our Q in. Our Q in was that weekly energy use of 100. And that was our Q out. Q out, so 100.9. We want to solve for Q in. So we know what we want out is 100.9 kilo-BTU. Why am I right? It's just getting messier and messier. We want 100 kilo-BTU, 100.9 kilo-BTU out, be able to heat our house during this week. So because we only get 90% out from how much we put in, we need to figure out how much more do we need to put in to be able to get that 100.9 out. So rearranging the equation, then solving for Q in. Q in is equal to that Q out, 100.9 kilo-BTU over 90% or 0.9. And from that we get 112.1 kilo-BTU for the energy input that we need. And then just last step, finding the cost of that, acquiring that much energy. So we know that in this spot, gas costs $1.50 per therm. So so our cost then is equal to first starting with 112 kilo-BTU, but then converting to therms. So one therm equals 100 kilo-BTU, and then multiplying by $1.50 per therm. And that equals $1.68. And that's it. Are there any questions?
Oh man, so much work to get to that 168.
Yeah, it didn't end up costing very much. This is a small house.
I just, since we're finishing the review, I did actually want to show like one more thing about solar, unless someone wants to ask a question about Sierra's work. Sorry, for those of you still here. Okay. I would recommend that you get very comfortable with these solar path diagrams. From back when I took 140, I remember this was a multiple choice question, like matching up where you think they are on the Earth. So good to be comfortable with like all those things that Eric was talking about, where the equator solar path diagram is very symmetrical, what the southern hemisphere looks like versus northern hemisphere. This is lecture 10, by the way. And then this is also a really great example from lecture 10. This is, I feel like this would definitely be on the exam, knowing how to use a loft stack, like figuring out at 11 a.m. and the latitude, and looking at also the different values you can get from a sun path diagram. Anyways, yeah. Thanks for coming, guys. Thanks for sticking towards the end. We're gonna go eat dinner now.
Thank you.
Right. Yeah.
Thank you so much.
Cool.
Yeah, feel free to reach out with any questions that come up as you're continuing your studying.
Yeah, you can email us, your non-GSIs or your specific GSIs, whatever. Here's your resource, but we're also studying for finals, so sorry if we respond a little slow. All right, I'm gonna stop the recording now.